Welcome. Another day, another coding challenge. This stream is for entertainment purposes only. So let's see if we can uh, crack some coding problem under 40 minutes today. Hopefully, or it's not hopefully, so because most likely we will get the hard problem, but hopefully random generator today will be a little bit, easy on us, and let's just see. So let's go and select the problem. Pick one. Okay, it's a medium. Maximum number of eaten apples. Uh, likes and dislikes are mixed here. So meaning that might not be obvious what's the main challenge here. That's why most likely we can come up with the algorithm that solves the problem, but not optimal or something like that, or doesn't fully understand the problem. Whatever. Let's see. There is a special kind of apple tree that grows apples every day for n days. On the th day, the tree grows apples I. And we've got this. Apples that will rot after days days. Uh, okay. That is on day I plus day i's. This one I didn't get it. Okay. The apples will be rotten. So on days from now, uh, they're still fresh. The apples will be rotten and can be eaten. On some days, the apple tree does not grow any apples, which are denoted by apples obviously equal to 0 and days to 0. Okay. You decided to eat at most one apple a day to keep the doctors away. Note that you can keep eating after the first n days. All right. Given two integer arrays and apples of length n, return the maximum number of apples you can eat. Interesting. I think I got the problem. So the thing is, it's basically somewhat like a cache with expiration, right? And so we first fill the cache, but then we know that at some point, some of those apples won't be used. But let's see. So we've got apples 1, 2, 3, 5, 2. So first day, 1 apple, 2, 3, 5, 2. And the days 3, 2, 1, 4, and 2. All right, obviously on the first day we'll eat the first apple, so we don't care about how long it. On the second day we'll eat 1 apple, then 1 apple, then 1 apple, and so we know that we consume 1 apple per day, right? So basically then it becomes the mean function between number of apples tree produces and number of days it takes them to rotten, right? Because if it produces 10 apples, but they will be, they will rot in 1 day, then technically you will be able to eat only 1 apple out of these 10. You don't care about the rest. You can eat 7 apples, obviously 5 days here, and then one of these 5, there are 4 days. They grew on the first day, and the second day you eat an apple that grew on the second day, and the third day you eat an apple that grew on the second day. Okay. After these day, apples that grew on the third day rot. Okay. but that's okay because we have 5 apples, so it will be 1, 2, 1, 2, 3, 4, so 2 extra days after that, yeah. So, and then at the same time, these two will rot after 7 days. After 7 days, all apples will rot, so. Yeah, so, so okay, let's switch to the whiteboard. So I already see the key solution here. So how to find it? It should be linear, to be frank. It should be linear, but it might require some interesting data structure to have. So going to, so where is this whiteboard, right? So let's plot this example in a little bit different way. Can I, just out of curiosity, can I have just straight line, like this here? Nope. Right. Let's do just this then. So let's see days. Say not 0. We start with 1, right? Day 1, day 2, or we can say day 0. Doesn't really matter because it's we are software engineers, so we should start with 0. All right, so yeah, I can be psych at drawing parallel lines, but you can assume it's some geometry of negative curvature. So they're parallel, you just don't see it here, but we know there should be parallel. Two, three, 4, 5, 6, say 7, and 8. So what do we want to do? You're basically plotting these apples and then assuming that we eat 1 apple per day. That's our problem, right? How many days we can cover at every day we grow the apples until they rot, right? So on the first day, so it will be mean function between the number of apples we grew and the number of days they last, right? So something minimum between them. Although it's not necessarily, right? Because if it's 1 apple, so yeah, let's actually just do it like this. So we have, but only 1 apple, right? So then we have, what, 2 apples starting from day 1 that last 2 days, right? This is 0, 1, 2, 3 days. These 2 days, so they should end at the same time as this one, but we have 2 now. All right, so then we go to the 3rd day. We produce 3 apples, but they last only 1 day. So, okay, let me draw it like this. It's like 1 day. So we know it's, so they should be like aligned here, all of them. So let me fix this thing. Now, so, right, so they're aligned here. So they expire at the same time. Then we have day 3. Right, so, and let's start from here, also from the middle, which is the 4th element. So we have 5 apples and they last 4 days. So it starts from here. So it's day 1, day 2, day 3, day 4, right? So 1, 2, 3, 4. Yes, correct. So those are 5 apples. And then we start um, at most 1 apple a day. So if there is no apples during the day, we may not eat and wait until the new apples will grow. So it means we will go through the entire timeline, right? Through every apple. So it doesn't make sense for us to reverse them. Okay, so and on the last day, on the 5th day, we grow another 2 apples, which last 2 days. So basically 1, 2, oh, okay, yeah. So they basically it doesn't matter. We cover this by this guy, so we don't need to. So we can go by every day, right? Let's use different color here. Say blue. So we start from day 0. I have 1 apple. Then move to day 1. We have 2 apples. So on day 2, we have 1 apple from that day, right? Plus 3 apples. So then we move, right? So we count this is 1, this is 1, this is 1, because we can eat 1 apple here. So when we move to day 3, actually none of these got transferred, but now we've got 5 apples. So we are fine, we get 1. Then move to these, day 4, we got 4 plus 2. So we can plus, so then we'll be, I don't know which one we eat, it doesn't really matter. Let's say 4 plus 1. We got 1. Then we move here. We've got only, so this one will rot, so it doesn't go here. And here we left 4 apples, right? Let's say we eat 1 more here again. So it's 4, and it's 1, 1. Once we move, then this will be 3. Actually, this one is, okay, it's expired, so we don't transfer. So after all, we left with 4 apples, right? So we eat basically 1 apple here and 1 apple here, then 1 apple here, 1 apple here. This one, any, it could be 3, whatever, it doesn't matter which one we eat during this day. During this day, we eat this one and then this one, right? So every day we eat 1 apple. Okay, so 7 days result. So that's the algorithm. We start counting how many apples, and then we need the function to tell us that, let's say on day 3, right, we might have this amount of apples expired. So we subtract it from whatever amount we have, right? So every time we move, we subtract whatever apples are expired, and we add them to the queue. So the question is, how do we track this thing? So the algorithm is this, right? This is basically the way how we do it. We do it step by step. So we need to track 2 things. we need to track new apples, which we already know how much apples we will produce new apples, and 2, when they expire, and 3, which apple we eat first, right? This might be not obvious. So we definitely won't eat those apples that expire first, I would say, right? All right, so let's see. Let's see if we can code this algorithm. Let's switch back to the default scene. All right, so what do we need? But does it really matter if we eat just one apple per day? I mean, which apple we eat first? We just need to add to the apples and subtract from the apples. And if this number is greater than 0, then we are fine, right? Because if at least one apple per day, we eat it. I see, yeah. But then next day we don't know how much apples to subtract unless we sum all of the apples been produced so far, and from this number we will, subtract all apples that were expired by that day, right? It's actually can be a good thing. So we just keep tracking all apples we have, right? Just keep adding it and then keep subtracting every time we have something in the expiration pool. And that's it. And keep iterating while what? While no apples left. All right. Then we need to do this thing. So first of all, let's see what are the inputs here. So the length is n, both of the same length, so we don't need to check for that. N can be at least one, so we don't need to check for 0. Apples can be from 0 to whatever, right? And day 0, if and only if apples 0. So then the only first condition we may check if apple size equals 1, return what? Apple 0 greater than 0, then 1, otherwise 0 days, right? So that's it. So this is one corner case that we don't need to worry about. So what would be the end condition? I see. So let's say int num apples. We start with 0, right? And let's say int day. We start with 0. So what we say, while num apples greater than 0 and day is less than apples size, which means if we don't have apples available, right, and no more apples will be grown on the apple tree because the season ended, we can stop. All right. So this will be at most O and plus whatever max days something. I don't know. It's asymptotic complexity, right? So whatever maximum value in days we have, plus n, this will be the maximum number of iterations we can make. So with this maximum number of days at the end of the tunnel, let's see. So, all right, let's also have unordered map of type int expiration day, right? So what this map will track, how many apples will expire at specific day, right? So as they said, it will be I plus days I as the key and number of apples I as the value. Although if we know the days, do we need the map in this case? So I'm just curious. So we start like this. So every day num apples plus equal int let's go CNT, like how many days we have apples, or fresh apples, whatever. Nowadays we just simply say as apples. We don't call it I, maybe we should call it I. All right. So so add new apples if season, right? So we say if I less than apples size, we add number of apples, right? So now we need to subtract expired apples, which is yeah, that's why we need the map, right? Which is basically if expiration day The only problem with this algorithm, we don't know exactly which apple we eat. But in theory, we say find what? Day I, right? Not equal expiration day and then num apples minus equal expiration day I, and then if finally if num apples are greater than 0, we say num apples actually at this point is okay. Num apples minus cnt plus, and at the end we say I plus, right? We go to the next day. And once cycle is ended, we return cnt. So that should be the straightforward algorithm. But the problem is we don't know which apple we eat exactly, right? From which day. Because the truth is that if you eat an apple, but we eat one apple per day, does it really matter? Does it really matter? So let's go through our example on the whiteboard we had using our code. So I will switch to the whiteboard and we'll use the code you saw. Just to go step by step, right? And maybe we will find the clarity here. So at day 0, let me say here, expiration map, right? So we have what? At day 0, we put 0 plus what? Plus 3, which will be 3, right? 3, and 1 apple will expire at day 3. Then, yeah, I already see the issue that it won't work, right? So then, once we eat this apple at the end of the day, we should make this 0. So we should decrement it here. But the problem is if we eat apple, which apple do we eat really? So if I always eat apple that was produced at the current day, let's say current day produces 1 apple, but it lasts 10 days, so I can eat it really the last one, right? Should I subtract from I should always subtract 1 from that apples that expire like tomorrow, right? Because tomorrow it doesn't really matter already. We should subtract whatever we had. All right. Always eat apple that expires tomorrow or best available, right? That's what we say. So should we then put them to the queue based on expiration date? So every day we put it to the queue based on, and the queue is based on expiration date, and then every time we pull one element from there. So we put the pairs, let's say one apple that expires at this day, or three apples that expires at this day. So if it's just one apple, then we completely remove it from the queue. If it's, let's say, three apples, then we, let's say, subtract number of apples available per this day, right? And in this case, it will be n log n. And let's see what are the combinations here. So it seems like we're using Q here. So we have, so the n is 20,000. All right, so it's not that bad. But then how do we track yeah, it makes sense. Okay, so I see. Let's do this then. Priority queue. So we have pair of int apples to x, or let's just call it q, whatever. So expiration day 2 apples. All right. So then we don't need this thing, frankly. Then, and we don't need, do we need I? I don't think we need I. Or maybe we do need I to see what's the day it is, right? Let's keep, we don't need most likely number of apples, but let's keep all of this, right? So in this case, because we retrieve one element, it will be this thing, all right, of log, whatever, n days. In the worst case, we put n elements to this queue. So we start like this. If I less than apple size, right, then we add apples to the queue. And actually, we never put apples to the map. So, so we say queue insert, oh no, sorry, push. I guess it's push top and pop for priority queue. I need to check CPP priority queue, CPP priority queue pair, CQ pair sorted by first. So if I do make pair, what it will give me? It will give me 20, and then output 20 and 100. It starts with the largest one and then goes to the lowest one, right? And we need vice versa. To make it vice versa, so it's, yes, 10 and 200, right? We say qpi, vector pi, pq make pair, greater pi. Okay, let's do this. Let's do exactly like this. So we do push and then top and then pop. Attention reader. So what's the pi is? It's pair. Yeah, let's do the same thing. Let's do the same thing. Let's have some namespace here. Space here. Let's define this pi. Should we call it pi or should we call it apples to whatever? Let's call it pi. I don't care. Greater pi pq. All right. So what do? We say pq push make pair. So we know that the expiration day comes first because we sort by expiration day. And then the second element comes number of apples. All right. So the expiration day is I plus days I, and we know that the size of day is the size of apples, so it should be never a corner case here. The number of apples is apples I, right? That's what we do every time. Great. Oh, so we don't need map anymore, so we don't need this crap. So all we need is to check that if PQ let's do this, remove road apples, right? So how do we do this? Basically, we need to say while PQ empty, right? While PQ is not empty and PQ top, right? So because, yeah, PQ top, because they may expire in multiple days, PQ top first less or equal that I, right? Less or equal that I, because that gets expired on these days. We do PQ pop, right? That's what we do. Then we add if a season, right, to the PQ. Then we say if PQ is not empty, right? Then we do this. And PQ top so if it gets 0, if it's just one apple and it gets to 0, we need to remove it. That's all we do, right? If not, we need to subtract it. We need to say, okay, PQ top second minus minus. That's what we do. If PQ is not empty. All right, so we know that there can be no case when the PQ second is 0. Unless, all right, so size is this and apples I greater than 0, right? So if new apple, add new apples if season, so we don't add empty apples. So we always know that we can CNT plus 1. And before we do this, we say this. So if that's what we do. Simply PQ top second minus minus, right? Then we check if PQ top second equals 0. We say PQ pop. That's it. Then we add int and then we subtract 1. So we don't need this one. All right, should work. So how much minutes? All right, we're about the completion time. So let's see. Oh, I didn't switch this in, so we haven't seen the code. Whatever, that's the code. Expiration date to apples. Priority queue. And let's also print C out here. So expiration day. pqtop first, right? And then we say num apples. We can also start with day. To ease the debugging process technically. Day what I, right? Expiration day, num apples, whatever. Here it will be pqtop second. We don't need this one here. pqtop second. And then we say new line. Right, run the code. Let's do error-driven development here. Oh yeah, we don't have num of apples. We need to just to say pq is not empty. While pq is not empty, right? Or if it's empty, then I is less than apple size. Okay, so that should work. Let's see. Oh, I guess make a pair should be like this, right? Mutable top. Let's see. CPP priority queue, mutable top. Yeah, so technically here, what we need to do, we need to first say pop, right? pq pop, so have this pair, pi, sorry, pqtop, let's say pi pqtop, then we say pq pop, pop, right? And if pi second, so where do we subtract second then? We subtract it from pi second minus minus. If pi second equals greater than 0, we say pq push. So we push it back. So at most it have 2 log n operations per iteration, which is fine. PI is the type, right? PI PI P or something, I don't know. Yeah, no, bad naming, I know, but push P. P second greater than 0, push P. Let's see if this works. Run code. All right, seems like works. So we start with day 0. Expiration day 3, now apple is 1. So on day 1, yes, we have expiration day 3, now apples 2, right? Because if we're returning back to this whiteboard, that's exactly what happens here. We put 2 apples, right? So they expire on day 3. So on this day, they got expired. Then again, the day 2 here, we still have just 1 apple left. Interesting. Yeah, we used 2 apples, I guess. That's why. Sounds a little bit weird. It should be like 1 apple we've added on day 3, which expires like in 1 day. It was 3 apples that expires in 1 day. So they expire on day what? Day 7? That's not the entire queue. So what I see here is not the entire queue. It's only what's on the top, the first one to expire, right? Then day 7, then we have some apples on day 6, as we said. So we're first subtracting these from day 6, and then we return to day 7 until they all got expired. And then the output 7. All right, looks good to me. So let's see. Let's just comment out this thing and submit. Weird. Why is that? Why the output is 1? 20,000 and 20,000. Okay, let me see what's went wrong. Technically, we should subtract it every time. So submit. Let's see one more time. I'm not sure why it didn't added it back to the queue. We subtract 1 apple only from the second one. Oh, it's a stupid corner case here. Yeah, so see, it should be days. Days I then. Day 0. We don't care, right? If it will be 0 if apple is 0, so we can just say this thing. So let's comment back this part. So this still should work as intended. But let's see if we pass time limit and it's accepted. Oh, come on, seriously? In this case, it will be mean. I don't think we really need to bother ourselves with this corner case with 1. Yeah, let's not bother. Let's just go full on our full-fledged solution. Let's not bother. Let's see if it works. It should work even like that. Ta-da! Stupid corner cases. Well, we're definitely not the fastest, and our memory not the best. But hey, it works. So we use 2 integers and 1 priority queue that uses pair of 2 numbers. So yeah, this one is, I guess, the most expensive part. In terms of memory, we don't need this any longer, so we can just say this. So we also copy element here. We do some interactions here and see if we want to put it back, whatever. Apple. All right, so we can say those are const because we don't modify them. It won't change anything anyway. And because we run out of time, I won't do any further improvements to the algorithm to try to improve memory or complexity. I will just run it several times to see what's the best numbers we can get. Sorry, submit several times to see what's the best numbers we can get. Yeah, the Q is, you see, it can be 176 milliseconds, can be 300 milliseconds. So far, it seems the first one was the best one, but let's see. Yeah, let's try to get these numbers again. Okay, we return back to the minimum memory we had, which is 65 points, which is great, but the time complexity is not great anymore. So let's see if we can improve it. So what I've done, I added const qualifiers, and this made compilation worse. Interesting. Nope, doesn't really matter. Oh, come on, give me this 176 milliseconds, 268, still small. It was 50% here. Memory was better. We've got memory 47. So ideally we get this number and this number, right? So these are the best options, or close to this, I don't know. Nope. All right, so seems like our scores won't be as big today. But hey, at least we cracked the problem and it's accepted. All right, so let's just submit one last time, maybe. No. Yes, almost as great as the first time, and it's 47 megabytes, so the memory is better. So yeah, I'm fine with that. It's actually more than 100 points together combined. So go to whiteboard scene. So today we have 46 points for time complexity, which is not the best one. I would imagine there is a better way of doing this. And 65 points for space. So together we have very cool number. Oh, nice. Like this. Done. Right. So because it's already almost 1 hour, so no fireworks today, but hey, we done it. Cool. And hopefully see you tomorrow. Thanks.